Really early on in my lab, we had this idea that I knew was very, very hard, and it was clearly the riskiest thing we would potentially start. And a postdoc applied to my lab, and he was a really talented scientist, and I told him at the beginning, I said, look, this is the most exciting idea I have. It is also the hardest. It will likely fail. Are you sure you want to work on it? And to his credit, he said, absolutely, this is what I want to do. And we started down this path, and really after a year of constant failure, I started to get really nervous. I started to get really nervous really for him, right? Because I felt a responsibility for his career. And luckily, he was a bit more stubborn than I was. So he just kept on this path and said, I really think we have something here. And it was about 2 weeks after the conversation where I said, maybe we should change from this project, that he came in with a seminal result. And it was kind of that kicked off, a lot of the research that the lab now pursues, right? Sometimes that one breakthrough can kind of open up, and that project has now trained like numerous PhD students and numerous theses, right? All from this one initial idea. And that's what was so critical about receiving the Beckman Young Investigator Award from the Arnold and Mabel Beckman Foundation. Really the confidence that it provided my lab to know we were on the right direction. And the problem that inspired me was the environmental and societal costs of plastic waste, right? This has become more and more prevalent as we produce really an insane amount of plastic. Each day we produce enough plastic pellets to fill a modern football stadium all the way up to the top, right? And that's 365 days a year. So the question becomes, what do you do with all that material? That, right, stands in contrast to the fact that we continue to need new materials to solve pressing challenges, right? To advance things like battery technology, so electric vehicles and transportation becomes more efficient. To continue to advance biomedical technology using polymers. So the idea, right, that today's materials won't solve tomorrow's challenges, but the new materials we make have to be sustainable and have to start to mitigate the environmental cost that plastics currently have, really is the dichotomy that we wanted to solve. In approaching this problem, right, I think something scientists do really commonly, right, is we try to use all this knowledge we've generated to continue to increase the complexity, right, of the solutions we have, right, and continue to kind of add on additional things to get, new function or more function. But when you're hit with this challenge of sustainability, you actually have to start thinking differently. You have to start saying, maybe we should start from the beginning and take really simple building blocks that we can potentially derive from biorenewable resources, and how do we build complexity with those really simple building blocks? So approaching this problem, right, using these really simple building blocks, we needed a way to engineer complexity. And the way we chose to do that was using what's known as catalysis, right? Or one molecule that essentially enables you to connect thousands of other molecules together to make these plastics. And we thought if we could engineer this catalyst to really specifically arrange each of the atoms that goes into making this plastic in space through what is known as stereocontrol, we could then use that, right, precision of connecting these molecules together to derive the complexity we wanted. So stereocontrol effectively is, right, the arrangement of atoms in space. And one common example you can think of is your hands. They're mirror images of each other, but they're not superimposable. Right? So if you took your right hand and connected it to your left arm, right, that would be all backwards. And the same thing happens with organic molecules, right? They have what is known as chirality. And it turns out that, controlling whether you have a right-handed molecule or a left-handed molecule is really important to its function. And in a plastic, what you want to do is you want to take these building blocks and connect them together. So you have to control the stereochemistry at each building block thousands of times, right, to make this plastic. And that turns out to be a really tricky chemical challenge that has been hard for generations of polymer chemists to solve. So our approach to this problem was to leverage electrostatic interactions, or the attraction of negative ions to positive ions. And we felt like if we could make a polymer where, right, the growing polymer chain always had a positive ion on it, we could use a negative counterion that actually had defined stereochemistry to really control the stereochemical environment around that growing polymer chain, and then dictate the facial addition of incoming building blocks. This had been used in the pharmaceutical industry for about a decade previously, but had never been translated to the production of plastics that we thought would be enabling. So We designed our first catalyst, right, that did have this chiral counterion. But for about a year, we were really running up against a wall. We kept kind of changing the structure of this catalyst and kept getting the same bad results, and to the point where I had to have a conversation with my postdoc saying, you know, maybe this project is too risky. The bar we were trying to hit is this 90% kind of stereo control. And 2 weeks later, he came with a piece of paper, I clearly remember, and he said, here is the first polymer actually ever created in the world of this that reaches that threshold. And that, I mean, I kind of, you know, in that moment and moving forward, it kind of like a lot of the work I'd put in over the past 10 years really started to fall into place. And that kind of led to a whole multitude of different advancements and things with the lab. So the key advance that we realized we made after we started to control the stereochemistry of these molecules is we were able to create a polymer, again, from a simple building block. And every other time people had created this polymer, you connected all these monomer units together, and if you didn't control the stereochemistry, this was just kind of a viscous liquid at room temperature. It felt like honey. What we found is when we did control the stereochemistry, we took that same material, so they're chemically identical, they're what we call stereoisomers of each other. But if you control the stereochemistry, you now get this solid, crystalline material that actually, when you press up a film of it, it actually feels exactly like a Ziploc bag. So again, we took a material that, you know, a simple building block that was bio-derived, and we made a material that had the same properties of polyethylene that you derive from petroleum. But in fact, as we looked into this a little more, this actually adhered to polar surfaces, things like, you know, glass or aluminum, you know, 10 to 20 times better than that same polyethylene that makes that Ziploc bag. A lot of people around the world have kind of adopted this concept of chiral counterion catalysis now to start to control stereochemistry. And my lab is to continue to push this forward in what we think are really exciting and unique ways. Again, all coming back to being catalyzed by that initial investment and confidence that the Beckman Young Investigator Award provided. What inspired me personally as a scientist from Dr. Beckman's career is his pursuit of this use-inspired basic research. So again, the fundamental contributions he made, especially in analytical chemistry and instrument development, right, allowed many others to pursue scientific problems that were of interest to them and really harness the creativity, right, of both the US and really the entire world to push our society forward. Really, I've taken into account, as I've learned and understood more about his career, is this philosophy of making fundamental contributions to science, but really connecting that to a societal need that then we can pursue in my own lab, but hopefully my lab can provide the tools for many other scientists around the world to pursue those pressing problems and hopefully unleash the creativity of far more than just myself.